You are given an array and you can select any set of indices and you can color them in red color. So in this example, 3 elements were chosen and colored in red. Then you can consider all of these elements that are colored in red as a barrier. This means that it will divide the array into disjoint subsegments. So this is the first segment which is colored in blue, and then there is a barrier. Then this is the second segment which is colored in green. There is a barrier. And the third segment where all the elements of a segment will colored in the same color. So this is the third segment which is colored in white, and then there is a barrier. Now you have to compute the sum of elements of the same color. So you compute what is the total sum of this segment, what is the total sum of this segment because they are of the same color, what is the total sum of this segment, and another thing that you have to compute is the sum of the barriers because barriers are also of the same color, which is red. So you have computed the sum for each different segment that lie within the barriers and the sum of the barriers itself, and you compute the maximum sum out of the sums that you have computed. So if this is S1, this is S2, this is S3, and the sum of barriers is S4. So first of all, you compute this value max of S1, S2, S3, S4. Now you will notice that this S1, S2, S3 and S4 are not fixed. Why? Because you are allowed to choose as many barriers as you want and at any location that you want. This is just one example that I gave you. So amongst all the possible choices of selecting a barrier, you have to find a configuration that minimizes this maximum sum of. So this is the maximum sum of elements of the same color. So you have to minimize this maximum sum. So how do you solve this problem? So this is a difficult problem, but we will see that if we approach this problem with the correct tools and techniques that are available to us, then the overall solution that comes out at the end is pretty simple and easy to understand. So first let's start out by trying to apply a greedy approach and see whether that leads us anywhere. You can notice that if the first blue segment that you have to create, so where should you place the first barrier? Should it be here? Should it be here? Should it be here or here? Where exactly should it be? So suppose you want to place the first barrier here. This means that this element will form, these set of elements will form the blue element. So if you place the barrier far to the right, if you place the first barrier very late, then this sum might dominate and then become the maximum. So then you might say that, okay, let's place the barriers as early as possible so that we minimize the dominant sum. So you might say that, okay, let's place a red barrier over here and a red barrier over here and here as well and here as well. But the problem with this approach is, sure, you have minimized the sum of each of these segments, right? Because you have kept them very, very small, right? The total number of subarrays is very small. But if you place too many barriers, the problem with that is the sum of the red elements might become the dominating factor. So you see there is a trade-off involved over here. Placing too many barriers is an issue, but placing too few barriers is also an issue. So suppose if you want to place just 2 barriers, then this sum and this sum, this middle sum can become quite large. But if you want to place, let's say 5 barriers, then what if the sum of the elements of the barriers itself become the dominating factor? So that is why you can see that you cannot apply a greedy strategy over here. So some kind of dynamic programming will definitely be involved in this problem. But how do we exactly apply dynamic programming? But before we do that, before we jump into dynamic programming, you might have already noticed that whenever the problem asks you to minimize the maximum value of something, so it is asking you to minimize the maximum sum of something. So you can do a transformation where you ask this question instead. Okay, if I have to minimize the maximum sum of something, can I find, can I, uh, we can say something like, is there an answer less than or equal to, let's say, x? This means that instead of trying to minimize or trying to maximize something, let's solve a simpler version of this problem. That is there a way of placing the barriers at several locations such that if you place the barriers here, 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 and let's say here, is it possible that the sum of all the elements is less than or equal to x? Because if the sum of all the elements of each color is less than or equal to x, it means that their maximum is also less than or equal to x. So we want to answer this question first. Like, is there a configuration of barriers such that all the elements color should be less than or equal to x? And now we will see why solving this easier problem will help you with coming up with the correct dynamic programming approach. So I will not dive deep into what is the motivation behind trying to solve this easier version of the problem, because this originates from a well-known idea in competitive programming. I already have some videos on my channel as well on why this strategy works. But for now, let's assume that we are able to compute this answer. That is there an answer less than or equal to x? Meaning, can you create barriers? So let's write that down explicitly. So we are looking for this. So let's formalize this, right? And you want to know, can you place barriers such that the sum of elements of any color is less than or equal to x? This is the problem that we want to solve. Can you place some barriers where the sum of elements of each color, including the color of the barrier, which is this red color, can you place these barriers such that each sum is less than or equal to x? Now, before jumping into the algorithm to solve this easy version of the problem, let's see if we can solve the original problem if we have the answer to this easy version. Now let's visualize the number line and notice that this is like, let's say 0 and this is infinity. Okay, and this is x somewhere over here. Now if the answer to this question is yes, if the answer to this question is yes, that is there a configuration where the sum of segments of any color is less than or equal to x, let's call that configuration as C1. Let's call that configuration as C1. What do I mean by the configuration? Configuration basically means the position of the red elements have been determined, and that also determines all the positions of the other colored elements, right? Now if you have this answer, like, is there a way to place barriers such that the sum of elements of any colors is less than or equal to x? Now if I ask you another question where I take this number y on this number line that is over here, and I ask you the same question, but this time I will replace x with y. So I take this question over here and I will ask you this question: is there a way to place the barrier such that the sum of the elements of any color is less than or equal to y? So, what do you think the answer to this question is? Is it yes? Is it no? Is it maybe? Is it yes, no, or maybe? So you can see that, for example, now let me also consider x as, let's say, 20 and y as 50. So if the answer to this problem is yes, that means that you have a configuration where each element, where the sum of elements of each color is less than or equal to 20. Then if I ask you another question, hey, can you give me a configuration where the sum of elements of each color is less than or equal to 50? The answer will definitely be yes. Why? Because you can just reuse the configuration C1. Because if a number is less than or equal to 20, it definitely is also less than or equal to 50. This means that if the answer to this problem, where you want to find out whether every element can be less than or equal to x, every color can be less than or equal to x, then the answer to this entire range will also be yes. And how? Because you can reuse this configuration C1, because something is less than x means something is also less than or equal to x plus 1. Okay, but now what if the answer to this problem is no? Like there is no configuration in the world where this sum of elements of any color is less than or equal to x. Then if I ask you another question, and this time I give you this like 10. What do you think the answer to this question would be? Like, is there a way to place the barrier such that the sum of elements of all the elements of a single color is less than or equal to 10? Do you think the answer to this would be yes, no, or maybe? So if the answer to this problem is no, that is, there is no configuration in which you can find all the elements that are less than or equal to 20, then the answer to this will also have to be no. Why is this true? Because if you have indeed found a configuration where everything is less than 20, then when I asked you the question, can you find a configuration where everything is less than equal to 20? Why did you say no? You could have just used this configuration. So this means that if you have any number line that spawns from 0 to infinity, and if you have selected, like, let's say the midpoint of this number line, then if the answer to this is yes, there is a configuration that is less than or equal to x, then the answer to this entire range will also be yes. So the answer to this entire range will also be yes. And what about the elements on the left hand side? So if there is a configuration where all the elements are less than or equal to 20, do you think there is a configuration where all the elements are also less than or equal to 10? So you can realize that this condition is a bit restrictive, because just because there is a configuration where every number is less than 20 doesn't mean that every number will also be less than equal to 10. So the left side is a maybe, right? It can exist, it might not exist. But if the answer to this problem is no, like there is no configuration, and you have this x over here, and the answer to this problem comes out to be no, this means there is no configuration in the world where you can place red barriers such that the color of each element sum of elements of each color is less than or equal to 20. So if there is no configuration where you can achieve every element less than 20, is there a configuration where you can achieve every element less than 10? It is impossible, because if you can achieve that configuration, why can't you reuse that configuration when I ask you this question? So this means that if this answer is no, then this entire left hand side will also respond no. No need to check it explicitly. And if the answer is yes, then this entire right hand side will also respond with yes. And if the answer is no, then what about the right hand side? So this right hand side will respond with maybe. Why? Because if there is no configuration where all the elements are less than 20, then means that some element should be greater than 20. So there might exist some configuration where everything is less than 100 or 1000 or something like that. So this means that this nicely splits it into, you get something like this. You get maybe, and then you get all yes, or you get all no, and then you get maybe. So now you can already see that you can try to guess the answer X. So this is not exactly the answer, I would say. You try to guess what is the closest that you can come to figuring out what all the elements are less than or equal to, right? So you have the infinite number line, and it's not really infinite, because the maximum answer can be what? At most the sum of all elements. Basically, there is no barrier. So then the maximum sum of all elements can only be up till sum. So you only have to deal with this interval only. Now notice that if you are having this pattern where the suffix is a yes sometimes and the prefix is a no, then you can be smart about the choice X that you had made. And suppose you find the midpoint of this segment, and this is this midpoint, and you define this as, let's say, M. This is the midpoint. Now, if the answer to this midpoint is yes, so you know that the answer to this suffix will also be yes. This entire suffix is yes. But you have just found a configuration where every element is less than or equal to M. And your goal, remember, was to minimize the value of the maximum element, right? So if you have this configuration, going to the right will only decrease your answer, right? It will only worsen your answer. So in order to not make your answer worse, you don't have to look at this segment anymore, because you just found a configuration that every element is less than or equal to M. Every color is less than or equal to M. This means that you can discard this entire interval. But if your answer is no, this means that the entire left hand side will be equal to no. So if the entire left hand side is equal to no, you can simply discard that element, because you know that you will not be getting any answer. This means that every time you select a midpoint, you can discard one half, either the left half or the right half. So every time, if the length of the interval was n, next time it will become n by 2, then it will become n by 4, then it will become n by 2 to the power 3, and so on. So this sum basically comes out to be 1 plus. So this sum is basically, no, it's not really this sum. I mean, you can see that in log n steps, it will become n by 2 to the power log n, which is n, and then the length of the interval will finally become 1. So this means that if the length of the interval is finally 1, then every element is less than or equal to X, and X is the single element on the interval. And you know that everything that you have discarded along your way was of no use to you. This means that whatever is remaining in that part, every element must satisfy less than or equal to X. In fact, that condition has to be more restrictive, and one of these sum will definitely be equal to X. And that's why, and that's how you have found your answer. Because if suppose one of the sums is not actually equal to X, so if you are following this strategy and assume that you have found an x where the interval length is just one element. And suppose this x is equal to 20, and if you claim that there can be an answer where everything is less than or equal to 19 because no sum of 20 is achieved in this result, then you can argue that in the previous round you shouldn't have discarded the 19. So if you have discarded the 19, it means that the last element remaining that has to match the sum of at least one color. So this is how you this is how you can apply this trick. And so this is exactly known as binary search on the answer. So right now we have not started on the dynamic programming yet, but this is the binary search part where you guess the answer. You don't really guess the answer, you guess the answer to the different problem. Like the problem is, can you achieve a sum where the answer is less than or equal to x? Okay, and then you try to trim down the interval size to 1, and then you can prove that if the interval size is 1, sure, the condition says that everything has to be less than or equal to x, but you can actually prove that there is at least one sum that will be equal to x, at least one color with sum x. So this means that if you fix x, uh, this is this is for final interval, just so that you don't get confused. So this is for the final interval. This means that if you can solve this problem, like answering this question, like is there an answer where everything is less than or equal to x in f of n time, let's say, then you can answer this query log n times, and the overall time complexity would become f of n into log n. So we have to now come up with the algorithm to solve this problem, this reduced version, in some better time complexity. So now we will start the dynamic programming part of the video. So let's again reformalize the problem statement. So this time we are not looking to minimize the maximum or maximize the minimum or anything like that, right? This time we are just looking to answer this question. Given x, can you place barriers such that the sum of each color is less than or equal to x? We are trying to solve just this problem. Now, even if you have not understood the binary search part of this video, that is fine, because this part is independent of the binary search. You can treat it as a completely new problem, where in this problem they have given you an array and they have also given you a number x, and they are asking you, can you place barriers such that the sum of each color is less than or equal to x, including the colors of the barriers. So how do you solve this problem? Now suppose you have this array, and suppose you know whether the answer to this problem is yes or no. Like can you place everything where the sum of each element is less than or equal to x? Now you ask yourself, okay, if I know the answer to this problem for this array, what will happen if I append a new element to this array, right? You try to answer this question, what happens when you append something to the array, append just one element to the array. Now if you are appending an element, there can only be two cases. This element can either be a barrier, or it's not a barrier. Okay, so first let's consider the case where it is not a barrier. If it is not a barrier, what information do you need to figure out if it is okay to place this element without converting it to a barrier? Because what if the last barrier is over here, and the sum of these elements, they are of course less than or equal to x, because you have to find the answer. But if you add this element into this color, into this yellow color, then what if its sum exceeds x, right? it could exceed. So maybe taking it as a barrier, not taking it as a barrier might not always be valid. So what do you need to remember? Here you can see that you need to remember what is the last position of the barrier that you have placed, so that you can figure out, can you place this element as a barrier or not. So what are the things that we need to remember? We need to remember, let's write that down. We need to remember the position of the last barrier. Why do we need to remember this? So that we can determine if the element that we are just appending over here, can it be merged into the last color. And how can you determine that? You determine the position of the last barrier, and then you compute this sum, and you add this, and you check, is this quantity still less than x? If it is yes, then you can definitely place this element as this one. You can definitely append this element, and it will not change the answer. Why? Because every color on the left hand side of the barrier, they will already be satisfying this constraint, right? And the only color that could have violated is this green color, and you have already merged these two segments together and validated that these elements is still less than or equal to x, and you have not added any new barrier. So if you have the answer to this problem, and if you decide to keep this as not a barrier, then you can also know the answer to this problem, as long as you remember where is your last barrier that you have placed in this array in the optimal configuration. But what about the other case where you want to place an element, but this time now you want to place an element, you want to append an element, because every time an element has two choices, right? You can either place it as not a barrier, or as a barrier, right? But we saw that you can only place it as not a barrier if the color is not exceeding. You can only place it as a barrier, as not a barrier, if you find the position of the last barrier, and then you merge this segment and this segment, and you see that their sum does not exceed x. But if it does exceed x, it means that you have to now place it as a barrier. So if you want to place it as a barrier, so this is a barrier over here. This means that all the individual colors in this segment, this color, this one, everything will still satisfy the property that every color is less than or equal to x, because you have not touched them. But now you are adding a barrier, and barrier is of color red, right? This means that what is the color that can violate the constraint? It is this red barrier, right? So what else do you have to remember? You have to remember that for all the barriers that you have placed so far, what is the sum of the barriers, so that you can decide whether the sum of the barriers on the left hand side plus this sum, right, this element a of last that you have added, is this less than or equal to x? Because if this is less than or equal to x, then yes, appending this element is indeed feasible, right? So now you need to remember two things. We need to, every time we append an element, we can only append it if we know. We need to remember the last position of the barrier, and we also need to know the sum of the elements of the barrier. We need to remember the sum of elements, sum of barrier values, right? Basically the sum of elements at the red indices. So if you define a dynamic programming like so, you define dp of I, uh, last and sum, something like a 3D dp like so, that dp of I last sum represents the sum, represents whether whether it is possible to place barriers for the first I elements such that the last barrier is at last is at index LST, and the sum of barriers is sum. So sure, you can define this 3D DP and it will work, right? There is nothing wrong with it. Now, of course, the time complexity will then become O of n cube, right? So can we do something better? So to do better, you can notice that if I don't give you this parameter, if I don't give you this parameter in your DP, can you still solve this problem? Because previously we saw that when you want to append an element, so you have this array and you want to append an element over here, you you need to know the position of the last barrier, right? And then you also need to know the sum of all the elements of the barrier. But you can notice that if you are placing elements strategically, then in the optimal configuration that you have produced so far, you would want to minimize the sum of elements of the barrier, because the barriers itself are the elements that interact with all the incoming elements. Otherwise, all the sums that are in between, there is no need to minimize these sums. Why? Because they just have to follow the constraints that they should be less than or equal to x. What I mean by that is, you don't actually need to minimize this blue sum. You don't need to minimize this green sum. You don't need to minimize this white sum. As long as they are less than or equal to x, we are good. This means that if you can place a barrier strategically such that the barrier sum that you have created so far is the minimum possible sum, then this gives you the best chances of appending an element. Because when you append an element, if you do treat it as a barrier, then in that case, this element, the sum of barriers will still be the minimum value. But if you don't want to treat it as a barrier, then also you can still check the feasibility of that. So therefore, you can instead have a simpler DP definition like so. You can like write DP of I last represents the minimum sum of barriers, minimum sum of red elements, such that the last red element is at index LST. So then if you have this DP definition, you can still implement it, and this is also correct, and it will give you the time complexity of O of n square. But can we optimize it even further? So now notice that each time you are placing an element, you have placed the first I elements, and then you are remembering where is the last barrier, and that is why your DP is becoming a 2D DP, right? So can we also drop this parameter, or maybe this parameter? Like, can we completely drop this parameter, this last parameter? So right now it might seem impossible to even drop the position of the last barrier. Like if you forget the position of the last barrier, like how would you even do anything that we discussed, right? Because you need to remember the sum. So we said that, okay, even if you don't remember the sum, it's fine. You can just minimize the sum, so that you can minimize the sum and you can track it as a DP value instead of a DP parameter. So, okay, that was good. But then this time you are saying that we don't even want to track the position of the last barrier. So then how would you do anything, right? But it is actually possible to drop the other parameter as well. It's a bit counterintuitive, but I'll show you. So this time you define a DP definition. So in all of these DP optimizations, the one thing that is common is you have to encode things in the DP value, not the DP parameter. So this time we'll define a DP something like this: DP of last. So this time we'll only track DP where the barrier ends at the last element. Okay. So we'll define something as DP of last represents the minimum sum of red elements such that the last red element is at index LST. So this time we are actually not remembering the position of the barriers anymore, but I'll show you why we can still solve the problem even if you don't remember the position of the barrier. And this is a very common technique that is used in dynamic programming problems. That is, you intentionally forget about a parameter, but then you try to recover it. Okay, so we'll see how we can recover it. So when you're appending this element AI, so yeah, so suppose you are appending this element, then since you have lost track of where the last barrier is in the optimal position, you now have to make a guess of where the last barrier could be. This last barrier could either be here, or it could either be here. You have lost the information, right? So you have to try all possibilities of the last barrier. The last barrier could be here, last barrier could be here, and so on. So last barrier could be any index on the left hand side. This index, this index, this index, this index, this index, and so on. So suppose you have decided that this is the last barrier. Then you would want to compute the sum of all elements of all the, you want to compute the minimum sum of all the elements of the barrier such that the last barrier is at this location. And this is nothing but what we have been storing. We are just storing the DP last represents the minimum sum of red elements such that the last element has to be the, such that the last red element is at index last. It means that the last element has to be a barrier. So this part we have stored. This part also we have stored in DP of blue, right? This part also we have stored. So this means that if you drop a DP parameter, the solution can still be found, okay? But your time complexity will be more. Here it was very simple. Like you track everything in your DP parameter and then you can do the transitions easily. But this time if you want to intentionally forget the location of the last barrier, then you have to try all possible location of the last barrier and then take the one that gives you the maximum profit. So the time complexity will still be O of n square. Why? Because every time you append an element, so suppose you are appending this element, you'll go from right to left and you will consider each element as the last barrier location and you will keep going. So for each append, you will make O of n insertions, but at least you have a 1D DP now. So what is the benefit actually of dropping a transition and then trying to guess that dropping a parameter and trying to guess and recover that parameter? What is the actual benefit? So now I'll show you what is the benefit for that, because it helps you do some optimization, because the minimum number of parameters, the minimal parameters that you have in your DP, the less parameters that you have in your DP, the better you can optimize it. So that's why So that's why, see, in dynamic programming problems, like if you are a beginner, you might have seen some 3D DP, like, okay, DP of X, Y, Z represents something. Okay. And this is actually very easy to understand, very easy to figure out what's happening and what's going on, etc. But as soon as you make progress, you will see that most people actually drop the last parameter, and then they also drop the second parameter, but the time complexity doesn't change. But you might think that, okay, why are they doing it? This, is it on purpose to save on this space? Not really, because if you stick to this 3D DP approach, it will get very difficult to optimize thing. But once you start dropping parameters and trying to recover it during the transitions, then you can apply the powerful tools and techniques that you have at your disposal, basically some algorithms and some data structures, to optimize those DP. So let's see how we can use those techniques over here to optimize this DP transition. And this time, let me formally write down the DP definition so that you don't get confused. So the formal DP definition is DP of I is the minimum sum of red elements such that the last red element is at position I. Simple. This is the DP definition. For some of you, this might sound very obvious. For some of you, this might be a bit complicated, because if you have been following along from the 3D DP, so you might wonder how it is even possible to recover everything. So we'll see how we can still do that. Now you have this big DP array where you have computed all DPI, minimum sum of red elements, such that the last red element is at position I, right? Then when you append an element, you will try to guess where did you place the last barrier, because you are not tracking it in the DP parameter anymore. So your guess will either be this element or this element or this element, and you can keep going here. But at one point of time, you will have to stop your guess. Why? Because remember that the problem that we are solving is the sub problem where every color has to be less than or equal to X. It means that since the array elements are positive, then going from right to left, at some point, at some point, this sum will become greater than X. So you will have to stop. So the possibilities for the last barrier will form an interval, will form a subarray that is ending just before AI. So in this possibility, if you want to make this element as the last barrier, because you know that this time you are only computing DP of I, this time you are not even computing the possibility that this is not a barrier, right? So if you want to make this element as a barrier, you want to how do you want to so this is the last barrier, right? If you want to make this element as a barrier, this is the last barrier. Then where do you want to strategically place the second last barrier? Of course, it has to be in this region, but which one exactly? So you would want to select this second last barrier such that when combined with the second last barrier, the sum that it produces of the red elements, that has to be minimal. Why it has to be minimal? So that the future incoming elements can take the benefit of the minimum some red elements, because it provides more breathing room for the incoming elements. Because if you take a larger sum, then the next time you want to make a red element as your barrier, it might not be possible. So what you are essentially looking for is the minimum element, so minimum DP value on this subarray, right? You are looking for this min of DP on this subarray, right? And how do you locate this subarray? Basically, this is the position where the sum exceeds uh, a certain value. So now you can already see that to optimize this, you can simply query the minimum element on this range using segment tree, and you will be able to do the transitions for you will be able to append each element in O of log n if you know where this boundary is. So how do you figure out where this boundary is? Like, how do you know what are the possibilities for adding a barrier? So now we will see some two-pointer optimizations to this dynamic programming. So right now we have seen that, okay, if you drop everything from your parameter and try to recover it during the transitions, then you can use a segment tree to compute the minimum DP value and always take the minimum DP on this subarray. But now let's look at some two-pointer optimization for this dynamic programming technique. So you have this array and you want to append this element. So if this element is like, let's say I at index I, and suppose for just one time you iterate over to the left, and suppose this is the boundary that you have found, because after crossing this boundary means exceeding this green sum. So this green sum is exceeding x. Okay. So suppose this is the boundary. This time you have manually computed the boundary by making of and operations or whatever. But what happens when you append a new element, a of I plus 1? This means that this boundary can only shrink. Why cannot it grow? Because first of all, you added one more element to the last segment. And then since you have added one more element and this element itself was overflowing, like this element was it's indeed very close to becoming greater than x, then if you take one more element, it will definitely be greater than x. So this means that this boundary can only shrink. So this interval can only move to the right. So this is where two pointer comes into play. So you start the starting left segment of the boundary, you call it as L, and for the first element you compute this L by yourself, and then if this is the ith element and this is the I plus 1th element, when you append a new element, this boundary can only go to the right. So that is why the total work that you will do will be O of n only, because L is only increasing and R is only increasing. So L only increases, R only increases. So using this trick, you can find out what is the valid segment for which your DP I can be a possible second last barrier, right? And then you know that once you have figured out the segment, like if this is the segment, you can use the segment tree to compute the minimum value. But now we'll look at the last optimization for this dynamic programming problem that you can reuse in other problems, and that optimization is that the first thing that we have noticed is that every element, every DP takes contribution from the interval on its left hand side, which is a continuous interval, and then this interval only shrinks and maybe grows on the right hand side, but only it has this pattern, right? It can only shrink from the left hand side and it can grow from on the right hand side, and you are always looking for a minimum of all the elements on this interval. So this means that whenever you see this pattern, you don't actually have to use this segment tree. Why? Because you are not modifying any elements on the left hand side, because you are processing the elements from left to right. So you are only interested in the minimum element for the elements that you have processed. So what you can do is you can just keep a set. You can maintain all these elements in a min heap or a set, and then once you shrink the interval from this green to this blue, you delete some element from the set, and once you expand this interval, you add an element to the set. So this means that you can actually solve this minimum problem in O of log n using just STL sets. No need to use a segment tree. Therefore, the solution to this problem, to this complicated problem, is, so the solution to this problem is nothing but, first you do the binary search on the answer to solve a different kind of problem. And for a fixed binary search value, you define dp of I as what is the minimum sum of the blocked elements, because that is what actually matters. Minimum sum of blocked elements, minimum sum of red elements, such that the last red element is at position I. And by the way, one common trick that you can use is you can append a dummy value 0 at the end, and you can always color it as a blocked element because it doesn't contribute anything. So if you do this, then your answer will be dp of n, the last element. So this is a sentinel trick that you can use. And for each DPI, we saw multiple tricks to optimize it, right? We first started with a 3D DP definition where you want to remember what is the position of the last element, what is the sum of the blocked elements. So then we said that, okay, no need to track the sum of the blocked elements or the sum of the red elements, because you can just minimize that sum because that is the only thing that matters. Then we said that no need to even track the position of the last element. You just track, okay, if this is the last element, what is the answer? So then if you don't track it, you have to guess where the second last element is. And then we saw that once you have done this, you can use two pointer technique to determine what is this interval from where it will take the contribution from. And once you have determined this interval, you can either use a segment tree to compute the minima, or you can even use a set. In fact, this problem can also be solved in O of n for a given fixed binary search value x by using monotonic stacks, which is also capable of telling you the minima when you are just appending and inserting elements, because we saw that here we are just collapsing the interval, shrinking the interval from the left and expanding it to the right. So, and we just have to maintain the minimum value of this interval. So this part can be very efficiently handled by a monotonic stack to find the minimum, although that's not very important. And yeah, and once you have this, you can do the binary search and implement it. So right now I will show you my solution, because all of these might sound very complicated, very vague. So unless you see the implementation, you might not believe me like what I'm trying to do. So I have actually not implemented the set solution. So I will just show you the binary search idea, and I did not get the time to code the set based solution. So but you should still try to implement it on your own. So first I do a binary search to figure out what is the minimum answer, that is 0. Maximum answer is the sum of all elements, right? And then I try to break the interval by trying to guess the midpoint as one of the answers. Like I'm trying to find the answer, I'm trying to find if the answer can be less than or equal to x. And if it is, so if the answer is yes, then I know that this entire set will return yes, right? So I can just discard this interval and I can only focus on this interval. But if the answer is no, then it means that the answer for the left hand side will also be no. So I can discard this interval. So this will work in O of log n. And for any interval, any midpoint x, I have to check can the answer be equal to that x or not. So to do that, see, this is the final DP code and this looks very simple, but you will realize that even though the code is very simple, the idea behind it might not be, depending upon your level of expertise with dynamic programming problems. So I believe this is one of the best problems to strengthen your understanding of dynamic programming problems. So we want to check, okay, can you add the red partitions such that the sum of all elements of the same color is less than or equal to k. So we said that, okay, we will only track the last blocked element. We will not track the position of the second last red element. We'll say that only the last element is blocked. We'll compulsorily block the last element like so. Then you iterate over all of these elements, and then if you are trying to append dp of I, then you have to find the interval to the left hand side with sum less than or equal to x, right? And then you have to take the minimum dp from this region and you have to append ai, because you are adding the last element as all, you are always adding the last element as the red element. And if this sum is less than or equal to k, then it means that begin you have to begin one red element over here, and then you can find out this, the last element. Since you had added a zero value at the end, then the last element will represent the answer to the original problem, because if you add a dummy value, red value at the end, then the second last element can be anywhere, right? This is what the problem says, and all the possibilities are encoded inside of it. And to optimize it, you can see that you are just interested in the minimum of a subsegment on the left hand side. You can use sets to minimize it. So yes, this problem I would say is a bit complicated, but at the same time very, very educational. And I am not claiming that you will learn everything from this video, but at least I hope that this video pushed you towards the tips and tricks and techniques that you need to learn in order to excel in these kind of problems. So naturally, like, you will not understand everything that I've discussed in this video in one sitting, but if you try to solve this problem over a couple of days on paper, then you will finally understand how this trick is, why it is working, like why intentionally ignoring a certain parameter and then trying to recover it during the transition works, how the DP optimizations work, and so on.